Hey everybody, welcome back to another edition in geometry. Mr. Anderson here with you in section 11.4 today. We're talking about regular polygons and composite figures. So let's get started. Objectives, first of all, find the areas of regular polygons. And secondly, find areas of composite figures. All right, so let's start with the regular polygons. So what we're talking about here is the figure inside of this, okay? And so remember, a polygon has multiple sides, straight edges. Of course, we have this circle that is circumscribed around it. I think the main reason for that is to show the center of the polygon there would be the same as the center of the circumscribed circle, okay? So the center is directly in the middle of that polygon. Now this is something you may not have heard before, this word apothem. Okay, so the apothem, it's a segment that's drawn from the center perpendicular to a side of the polygon. So here, going from G straight to the side at a 90-degree angle, this is the apothem. Okay, so from G to H. So in this case, line segment GH would be an apothem there, okay? Central angle. The central angle, we've talked about that before with circles. Remember, the central angle went back to the center. That's the same thing here, but what specifically we're talking about here is it's the central angle going to the center, but the two sides of the central angle go through consecutive vertices. So, you know, from C to G to D, that would be a central angle, this whole thing here, and then the apothem splits that in half there, okay? And then the measure of a central angle of a regular n-gon, so that just means however many sides you have here. If it's an n-gon, remember that's short for however many sides there are. It's just 360 degrees divided by however many sides there are. So if this is a pentagon, that's 5 sides, the central angle will be 360 divided by 5. If it's a hexagon, which would be 6 sides, 360 divided by 6. So however many sides there are, you just divide by that to tell you the angle, the central angle here. So and that makes sense. If you drew lines every vertex here, you know, you've split, remember, 360 degrees is all the way around, and so you've just split it up. In this case, it's a hexagon, so 6 separate ways. Since it's regular, remember, regular polygons, all the sides are congruent, okay, and all the angles are congruent. So that's what regular polygon means. All right, so first thing is, let's just identify a few things here. In the figure, see in the figure, we have pentagon, PQRST. It's inscribed in circle X. Identify the center. All right, so let's do this here. Center. Radius. An apothem, not to be confused with an opossum. Oh, that's a good one. And of course, I almost wrote it, but apothem. And then a central angle. I like that though, opossum. Not a possum, apothem. That seems like that could be the tagline to like a really funny joke. I'll have to come up with that joke. Okay, so anyway, let's get back to this. The center, remember, is the point right in the middle. That would be X is the center there, point X. The radius that we're talking about here, remember, goes from the center to the side, one of the sides at a 90-degree angle, so XN is a radius there. Line segment XN. Oh, I'm sorry, that's the apothem. Let me just scratch that out. That's the apothem is XN because it's going from the center straight to the side. The radius, remember the radius, that's talking about the circle, so it's going from X to Q, or you could also say X to R. All that apothem joke stuff got me thrown off my game there. So anyway, the radius is XQ You could call that xq, or you could say xr would also be a radius there. Okay, and then the central angle would be this whole angle right here. Remember, the apothem splits that into two equal parts, so you could say QXR. So angle QXR would be the central angle. Okay, so just to kind of name a few things here. So let's get into finding some areas of these things. Okay, so this is a regular hexagon. And if you notice what's happened here in this hexagon, lines have been drawn from the center to each vertex. Okay? And so what we did was we split this hexagon up into 6 individual triangles. Say, oh, okay. Well, if I'm going to find the area of this, could I try to find the area of each triangle separately? Yes, the answer is yes. And since this is a regular polygon, when we split this up this way, all of these triangles will be exactly the same. So if I can find the area of one triangle, I can just multiply, in this case, times 6, since there are 6 sections there. All right, so how would I find the area of a triangle again? So remember, the area of a triangle is just 1/2 base times height. All right, well, now keep in mind as well here, let's look at this triangle down here. We've got, if we're looking at this triangle, this looks like a height, 1.7. Oh, I don't have the base. Oh, but wait, there's a 3 up here. If this is a regular polygon, all of these portions here, these line segments, will all be 3. So if I know that all those sides are the same, they're all 3, now I can find the area of this triangle. So let's plug this stuff in. So it's just going to be 1/2 3 times 1.7. Okay. All right, calculator. And so let's just go 3 times 1.7. And then remember what I can do, since it's times 1/2, I could just as easily go divided by 2. That would be just as easy. So it looks like 2.55. Now remember, that's just one triangle. So how many triangles do I have total? 1, 2, 3, 4, 5, 6. It's a hexagon, so 6. So what I want to do to find the area of the whole entire hexagon, I just take 2.55 times 6. And that will tell me 15.3. So that means I'm just going to find the area of the hexagon, it's just going to be 2.55 times 6. And so that was 15.3. And since it's feet, remember feet squared. Remember square units when we do area. Okay, so that kind of makes sense, right? You kind of see what's going on. All right, well, let me walk you through something here. I think I've got on the next slide. That leads us, what we just did leads us to this formula right here. Okay, this is the one that we're getting to. What did we do before? Remember when we did the one little triangle, we did the area equals 1/2 base times height. Well, the base is S, the side length. The height was the apothem. The apothem. Oh boy. So base times height is the side times the apothem. And I feel like I'm talking with a lisp. And so anyway, but then we had to multiply it by the number of sides. So that's what happened here. We said 1/2 A times S times N is the number of sides. And so if you look at this, though, that's what we did when we broke it down separately. But what's the number of sides times S? If I have S times however many sides, that gives me the perimeter. Okay, so N times S, the number of sides times the side length, is the perimeter. So this is our kind of our updated formula here that we can use for a regular polygon. Area equals 1/2 the apothem times the perimeter. Okay, and so that may be at times a little bit easier to use. So this is a new formula there. Let's take a look at that. I'm going to have the same kind of similar kind of problem that we just did, but let's use that new formula now. So same kind of a deal here basically, and it's a hexagon as well. It's just the numbers are slightly different here. But let's look at it with the new formula here. So the area equals 1/2 the apothem times the perimeter. Okay, so what's the apothem? 1.5. And the perimeter, all we do for the perimeter is, if you know, this is 2, 4, 6, 8, 10, 12, which was just 2 times 6. So we can just plug that right into our formula there, and that seems like that might be a little bit easier and quicker than what we did before. And so in this case, we're just going to go 12, times 1.5, which gives me 18, and then I'm just going to divide by 2. Instead of times 1/2, I'm going to divide by 2. And so it looks like we've got 9 there, so the area would be 9 feet squared. Okay, so there's our new formula that we can use for area of a regular polygon. This only works when it's regular, or all sides are equal. 1/2 apothem times perimeter. Now, I seem really excited about that. Sometimes you might get a situation like this, and there could be other things more complicated, but this is the most complicated we're going to talk about today. We've got a hexagon again here, and they've given us a side length, but we do not know the apothem. We don't know anything else about this. All right, so where do we start? What can we do here? All right, what we're going to start with in a situation like this is, let's figure out how many degrees this central angle is going to be. All right, so remember, there are 360 degrees total here, so I will divide by the number of sides. 360 degrees divided by the number of sides. And so that's going to be what? 60 degrees. Okay, so this is the central angle, 60 degrees. Okay, which is QPR. It's that whole thing. Well, in a regular polygon, this apothem, as I've said before, splits that central angle up into 2 equal parts. Okay, so what do we know? If the whole thing is 60, that means one of these parts here, I'm just going to draw an angle to this part here, that's 30. Now what else do we know? Now look at like this triangle to the right here, which is made up of the apothem, part of a side, and then this radius here. That's a right triangle. It's a right triangle. We know some things about right triangles, don't we? Excuse me. I got too excited. All right, so first thing that we know is if we draw this apothem, it also splits this side into equal parts. So if the whole thing is 5, just this part here is what? 2.5, right? Try to fit it in there. Now, excuse me. So if this is 30 degrees, this is 90 degrees. What's the degree of this angle that's left here? 30, 90, and 60. We have a 30, 60, 90 triangle. So we know some things about a 30, 60, 90 triangle, right? Remember our little pattern here? If we had a 30, 60, 90, there's the 90. This would be 60. This would be 30. And remember, across from the 30 was, we called it S. And then remember, this is the hypotenuse. Remember, hype it up. Woo, we're hyping it up. It's twice as good as S. It's 2S. And then the other side would be S squared of 3. So let's remember that pattern here to help us solve this. And so what we need to do is we go, well, the 2.5, if you notice, that's across from the 30. So the 2.5 is S. What we want to find out is what's the apothem. Okay, so that is not the hypotenuse. The hypotenuse would be this over here. That's this side right here. So we're just going to do what? 2.5 times the square root of 3. Okay, so this is the apothem. I'll call it little a there, which is going to be 2.5 times the square root of 3. Okay, I just plugged 2.5, since that's s in this figure here, in here to find this side. And then, so we just 2.5 times square root of 3. And in our formula here for the area, area equals 1/2 the apothem times the perimeter. Actually, let's find the apothem first. I'm sorry, I was kind of jumping ahead there. Calculator. 2.5 times the square root of 3. Okay, so that gives us approximately, we'll go 4.33 there. Okay, so this is our apothem, and so now let's go to our formula here, which will be 1/2 the apothem, 4.33, times the perimeter. What will the perimeter be? Well, it's 5 times 6, so 30. And this is what we'll plug into our formula here. And so I'm just going to use that original number since I've got it there already, times 30, and then just divide by 2. Again, instead of times 1/2, I'll just divide by 2. So it looks like our area here then is approximately 64.95 meters squared. Okay, so that's a little bit more complicated, but that is something that you can do if you don't. If you're missing some piece of information, think about that. You might be able to get a 30, 60, 90 triangle, or you might be able to get a 45, 45, 90 triangle and use our pattern here. Okay? All right, lastly, we're going to talk about composite figures. And so that just is oddly shaped figures that we're trying to find the area of, and there's no formula for this figure. This is such a weird shaped figure. But what we do is composite just means it's made up of smaller pieces that we kind of put together. So we're just going to see how we could split this up into smaller pieces that we do know the formulas for, and then just add them together, or in the next example, perhaps subtract them. So what I'm going to do here is, if you notice the way they've got this split up, dotted lines, this makes a rectangle in the middle. Okay, what's the area of a rectangle? Length times width. I don't know why I put that extra dot, but that's going to be 32 times 16. 32 times 16. And so, wow, okay. 32 times 16, it looks like that's 512. So I'm going to just go ahead and write it in here. So the area of just this rectangle that's outlined by these dotted lines here, just that part is 512. All right, well, what else do we have? Well, we've got a triangle down here. Hey, we know that a triangle, area of a triangle, is 1/2 base times height. Well, if this is a rectangle and that's 32, that means this is also 32 here. That can be our base. This is our height. So our base is 32. Our height is 15. So 1/2 base 32 times height 15. And so I don't know what's going on with my calculator here. 32, but I think it just got bigger. Did it just get bigger? 32 times 15 is 480, and then instead of times 1/2, we'll just divide by 2. So it looks like that's 240. So let's write this in here, 240 for that part. Okay, so we got 512, 240. What do we have left? We've got, it looks like half of a circle here and half of a circle over here. Okay, well, so what we can do is we can save ourselves a little time here. Since there's 2 half of circles, we can just treat that as one total circle, right? So remember, the area of a circle will be pi r squared. And so we just need to know what r is. Well, if you look here, 16 feet is this total distance. That's the diameter of this circle. So half of that would be the radius. So just this part here would be 8. And so we're going to plug that in. 8 squared, which is 64 pi. And so we can just type that in there. 64 pi is about 201. So it's approximately 201. We'll call it 0.1. And so that's the whole entire, this half and that half. If you only had one of these halves, you just divide this by 2, since you'd only have like half of a circle, just if you didn't have that. But since we've got 2 halves, we'll just keep this at 201. And so all we do to finish this out is you're just going to add 512 plus 240 plus 201.1. We probably could have just made that 201 and been happy with that, but 512 plus 240 plus 201.1. And so that, in the end, the area of this whole figure will be 953.1, and again, feet squared. Okay, it's a little weird looking there, but I think you get 953.1 feet squared. Okay, so square units again on the area there. Okay, one more. Let's look at one more here. In this situation, remember the last one we split up the little pieces and then added stuff together? Here, this is, to me, this is the coolest one of all, because we're going to find area and then subtract out this part in the middle, okay? So let's find the area of the big blue outside edges here. So with all the information that they've given us, we got 25, 25, and 20. So this whole side here is what? 50 plus 20, or 70. That whole side, well, it's going to be 125, and even though it's not written here, I think we're going to assume, since all of these are 25, that this will be 25 out here as well. That 20, I believe, refers to this measurement, not that measurement. So we're going to assume 125 and then another 25, so that's 150. Okay, well, that's a rectangle, so the area, I'm going to say, of the big rectangle is just going to be 70 times 150. And so 70 times 150 is 10,500. Okay, so that's the big one. Now let's find the area of the little part in here. So the area of the little part is going to be what? It's 100 and by 20. So 100 times 20. And so to finish this off, then we've just got what? 100 times 20. So 2,000. And then what we do is we just subtract that 2,000. And so this will just be 10,500 minus 2,000, and so that would be what? 8,500 feet squared. That would be the area of just the blue shaded section. So really, you know, pretty cool that when you're finding areas of these weirdly shaped things, that you can split it up into smaller shapes that you know, and then combine those, or subtract out holes. You know, like we had a hole in this segment here. If I can, I don't even know where my pen is. Over here. That's it right there. Okay, well, that's it. Mr. Anderson here in 11.4. Thanks for being with me. We'll see you next time. Hasta la vista.